Is this a continuous function on a closed interval? Starts at a point, ends at a point, draw it without picking up my pencil. Theorem says I have to have a highest and lowest point. My highest is here, my lowest is here, right? Give you another example. Okay, is this a continuous function on a closed interval? So start somewhere, end somewhere, draw it without picking up my pencil, right? It is a function, passes the vertical line test. So the theorem should apply, right? This function should reach its highest and lowest value. Does it? Is there a highest point? Is there a lowest point? Yes. They're the same y value. Remember I talked about this, like you asked, can you use a point? Yes, but when you talk about the max and mins, you're really talking about y values. So here, let me just give you, just for example, like this is the number 3, okay? What I would say here is that the absolute max of this function is what? Is 3. And where does it happen? On the entire thing, right? Where does it happen? And it happens at, well, whatever this interval is, I'll just make it up, 2 to, let's say, 4. So I would say at, I wouldn't want to say at because it's not happening at a single point, so I would say something like on the entire interval, right? At every point between 2 and 4, every point you ever plug in, you're going to get 3, right? So it's like you have an infinite number of places where it hits the maximum value. And then what about the absolute minimum? The same exact answer. The absolute minimum is 3, and it happens on 2, 4. So I'm giving you kind of like a weird extreme case here just to make you understand that like the theorem still applies, all right? This is really more what we're interested in, but I just want to show you kind of a weird case. Yes? Yeah, for local max and local min, you could say the exact same thing. Okay, extreme value theorem just guarantees that you have it. The extreme value theorem guarantees you have an absolute max and min so long as you have a continuous function on a closed interval. All right, the next definition is something that you, I think, have probably seen in the past, and that is the average rate of change of a function. All right, the average rate of change. So I'm going to draw a picture that goes with this. Let's say we have a function. Let's say oh, let me draw the function first. Okay, I'm going to call that function f. And I want to know if I started, let's say, at this point A, which would be right here, and then I ended at some other point over here, B. We're not talking about local max, local min, absolute max. This is something different now, okay? So if I have a function, right, and I start at some point A and end at some point B, I'd like to know what the average rate of change is. The average rate of change from here to here. So what I'd like to do is I'd like to label this. This right here is a point, right? The x-coordinate of this point is the A, and the y-coordinate, which is how high it is off the ground, right here, this, is what I get when I plug A into the function. Do you all agree? If I give you a function and I say, hey, what is happening at A? You'd plug A in, and that would give you the output. That's how high it is, yes? And this one would be the point, what? B, and then what's the y-coordinate? F of B. Do you understand that diagram there? The average rate of change, this is the definition of it, the average rate of change. The average rate of change is, by definition, we denote it with this symbol. Anyone know what that symbol is called right there? Yep. delta, and it stands for change, delta y over delta x. So this is the delta symbol. It stands for the word change. This is your change in y divided by your change in x. So if you imagine here drawing a right triangle that comes down like this, connecting these 2 points with a straight line, this geometrically is your delta y, and this right here is your delta x. This is how much to get from this point to this point, this is how much your y changes by. And then to get from here to here, this is how much your x changes by. Does that make sense? Change in x this way, change in y this way. So the average rate of change is the ratio of those two numbers, which back in college algebra you might remember as being rise over run, right? Rise over run, like the slope of a line. See, this is a line, isn't it? And the slope would be rise over run. So that's exactly what this is. It's just the slope of the line connecting these two. And continue, what is that? Well, your change in y. So how much do your y's change by? Well, here's where you stop, right? And here's where you start. So you start this high, and you end this high. So if I want to know this, it's the difference of the two. So all I do is subtract f of b, take f of b and I subtract f of a, and that gives me my change in y. And the change in x is however far you are here, take away this distance, and that'll give you the remaining distance. So you take that and subtract this, b minus a. And they put here at the end, a can't be b. Why? If a is b, right, then those 2 points are the same point, aren't they? And then you can't have a line through 1 point. Right? You need 2 points for a line.
And it's also divided by 0, right?
And you'll divide by 0, exactly. Okay, y'all got this? Yeah? Okay, so that's your average rate of change. I want to put this in context of something that makes a little more sense. All right, so I have to take my daughter to school every morning. I don't know if I've told y'all this. I drive 90 miles a day, about 80 to 90 miles a day. Yeah, I love traffic. So I leave my house at 6:20 every day, right? 6:20 I leave my house. So let's just say this is where I leave my house. This is time 0. This is going to be time, and this is going to be the distance. The time, let's measure this in hours. Somebody get a calculator out. Let's see, distance is going to be in miles. And here's what I can tell you. I leave at 6:20, and I usually get here at 7:30. Okay? I drive her to school and I come back. That is 23 plus, it's 23 miles to get her there and 18 to come back. So what's that, 41 miles? Okay, I have to do it twice a day, and then I have to get home too. So that's why I do almost 90 miles a day. So 41 miles just to get, so I did 41 miles and it took me what, an hour? Hour 10. Let's just make it easy for us, okay? Let's make it easy. Can I just say that we left at 6:30? We were running late today. That way it's only 1 hour? Okay, it's actually a little longer. But so what I can say is that in 1 hour, right, how far did I go? 41 miles. So I have that point and I have this point. Now, I drove, right? I was on 151. I was slowed down. I was going slow. I was hauling ass down 90. You know, like, so my speed is going up and down, you know, coming to stops, right? So, but I never like disappeared, vanished off the face of the earth, and then came back in a different location, right? So my path should be a nice continuous function through here, shouldn't it?
Yep.
All right, so maybe in the beginning I'm going slow, and then, you know, I speed up, and then I get stuck in traffic, and then, you know, whatever. And I finally get back here to work, right? That right there is a visual representation of my trip this morning. Now, what's my average speed? What was my average speed, which is the average rate of change? What's my average speed between the beginning of the trip and the end of the trip? So I'm saying this is kind of like the A, this is the B, right? And these are my 2 points. So my average rate of change should be f of b minus f of a over b minus a. So what is this point? 1 hour, how far did I go? 41. And then here, this is the point, this is an easy point, right? This is 0, 0. And so to find my average rate of change, I'll say average rate of change, which is my average speed. It'll be equal to what? Follow the formula. 41 minus what? Minus this, right? 0 over 1 minus 0. I know that you already probably could have computed this in your head, but I'm just showing you the actual. What's up? 1 minus 1, yeah, sorry. 1 minus 0. And so what was my average? 41, right? 41 what? Well, we did the y divided by the x, right? How do we measure our y value? Miles. How do we measure our x value? Hours. So we put here miles over hours, because it's a ratio, right? Miles over hours. And miles over hours is miles per hour, right? That's the way we say it.
See this in business too, right?
Yeah, yeah. So this is the average rate of change, right? Average rate of change. That's exactly what that formula is about. Now, do you all agree that if somebody gives you a function, right? Let's say I give you a function and I ask you for the average rate of change, it should be pretty straightforward because all you're doing is plugging numbers in, just subtracting, right? Here's the more profound question that we're not going to be able to answer. Right here. Let's say, I was partially through my drive at 0.25 hours, because this is measured in hours, I can't put minutes down here. At 0.25 hours, right there at that point, how fast was I going? Do you see that that's a different question? I'm not asking for the average speed. I'm talking about what we refer to as the instantaneous speed. How fast was I going there? So at 0.25 hours, I look at my speedometer and it gives me a speed, doesn't it? Right? How could we calculate that from this picture? There's a problem, isn't there? Like, how do you talk about the speed of something at a single point? You can't, right? You need 2 points, don't you?
Yeah.
You need 2 points. You need 2. So if I say what's happening at 0.25, you can't do it because you don't have a second point. Now, could you pick a point next to it, like right here, and then give me the average speed right there? Could you do that? Yes, but it would be an average speed on there would be a little increment of time there, wouldn't there? In calculus, what we do is we try and find a way to define the speed at a point. That's what calculus is about, really. And if we can find the speed of me at that point, then instead of finding the line connecting 2 points, we found the line that goes through 1 point. That's where you're headed, down the road, all right? I'm just trying to preface it with this example that I think most people can understand because we all drive, right? Or in cars. So here's an example for us to work on. Do I want that one? It was a pretty basic one. Let me see. Yeah, let's just do it. So this is an actual example. We have the formula. I'll leave the formula right there on the board. Oh, this red doesn't like to come on. All right, average rate of change. So I'm giving you a function. This is given to you, f of x equals 3x squared. And part A, we're finding the average rate of change from 1 to 3. So what this means is they're giving you the x values, all right? This is an x value, and this is an x value. So visually, it looks like this. We don't need the visual to answer the question. I just want to make sure you understand it. So they're giving us from 1 to 3, they want to know the average rate of change. So first thing I'm going to do is figure out what happens when I plug 1 into this function. So what happens if you plug 1 in right here? It equals 3. So that means here at 3, if I plug in 1, I get 3. right? And now I'm going to plug 3 into that function. So when I plug in 3, what do I get? Point way up here. What is it? 3 squared, 9 times 3, 27. So not drawn to scale, but yes, you see it? Now, what the function actually does in here, like if you graph this function, it's not a straight line. If you graph it, it's actually a parabola. That's not relevant. What we're trying to do is we are trying to find the average rate of change. So we're trying to find the slope of that red line that connects those 2 points together. So what is the slope? What is the average rate of change? It's this. Okay, so the average rate of change right, for part A is, okay, what's f of b for us? 27 minus f of a, 3 over the b, 3 minus the a, which is 1. So this is a, f of a. This is b, f of b. And now you just calculate that. What is it? 12. And we're not going to say miles per hour or anything like that because this isn't a car or anything. This is just a graph. So 12. That is the slope of that red line right there, 12. All right. How about from 1 to 7? Let's do part C. From 1 to 7, the only thing that changes is that you're still here at this point, what, 1, 3? But now you're at 7, and what's that point? Because you got to do what? 7 squared? 49 times 3? What is it? 147. 147. All right, that's just plugging 7 into the function. This is your a f of a. This is your b f of b. Calculate the formula. You're going to get what? 147 minus 3 over 7 minus 1. 144 over 6. Does it go in? 24? Yeah? 24. Okay. Any questions there? Average rate of change. Someone gives you a function. They want to know the average rate of change from one place to another. Those are your x values. Or you could say that's your a and that's your b, and then you plug them in, you do your little formula, and you're done. Next definition. Last definition. And do you see, I told you all about that symbol, right? That symbol right there means that this is a calculus topic. So when we look at a function, right? I'm not going to draw this on the board. When we look at a function, this blue function here, if we were to pick a point A and a point B, we just saw how you could find this. We just saw that you could find the slope of the line connecting these two, right? Connect these two with the line. We said we could find that slope. This line that connects the two together is called the secant line. It's called the secant line. And that's all this definition does, is it tells you that's what it's called. All right? It's called the secant line. So to find the slope of the secant line, right? To find the slope of that secant line, all you're going to do is calculate the average rate of change. So that formula right there gives you the slope of that line. All right, it's time for us to do a problem like that brings this all together. But before I do it, I have to make sure you know how to do something. And what I'm about to put on the board right here, I always start my Cal 1 class first day. I make sure they understand this. I ask them to recall this from a previous class. So let's say, all right, I'm going to give you some instructions here. This is how to find the equation of a line given 2 points. All right? I'm about to make sure you understand how to do this, because this is fundamental. This is a fundamental concept that if you can't do this, you'll have a little bit of a problem in this class, but in calculus you'll have major problems. All right? So if somebody gives you 2 points, can you give me the equation of the line that goes through those 2 points? That's what we need to be able to do. So visually, if somebody gives me a point, let's call this point A, f of, let's not call it A. Let's go even more back further. Let's call this one x1, y1. And let's call a second point here x2, y2. The reason I'm not putting A, f of A, and B, f of B is because I'm not talking about a function right now. All I'm talking about is, hey, if somebody gives me 2 points, can I find the equation of the line through them? That's all I'm saying. So here are 2 points, x1, y1, x2, y2. All right, to do this, you must know this. You must use what is called the slope-intercept formula, which is y minus y1 equals m times x minus x1. Show of hands, how many of you that looks somewhat familiar? Yes? That is what's called your, wait, I wrote the wrong damn thing out there. Sorry. That's not the slope-intercept. I'm thinking of my other class. Point-slope formula. Point-slope formula. What this formula does is it allows you to come up with the equation of a line as long as you were given what? A point on the line and the slope of the line. If you have those 2 things, then you can find the equation. I'll do this in red. So what is the point in this equation, this formula, what's the point that I'm given? x1, y1. That's the point that you have to be given. And then what's the slope in this thing? This right here is your slope. So if somebody gives you the slope of a line and they give you a point on the line, all you do is plug into this equation and you're good to go. You have the formula. So if somebody gives us 2 points, right? If somebody gives us 2 points and we want the equation of the line, this formula tells us how to do it if we have 1 point. Do we have 1 point?
Yeah.
We actually have 2, but we have 1 at least. And do we have the slope? So if I give you 2 points, do you know the slope? Not directly, right? Not directly, but could you calculate it? Yes. How do you get the slope of the line connecting these 2 points from this picture? So to find the slope of this line connecting, we do the same thing we did before, right? Rise over run. The slope of this line would be m, we'll call it m, is y2 minus y1 over x2 minus x1, which is the exact same formula we just had a second ago. We're taking this, subtracting this, and we're dividing by this, subtracting this. So recap, if somebody gives you 2 points and you want to find the equation of the line, here's what you're going to do. You're going to calculate the slope. And once you have the slope, you're going to plug that number in right here. And then here you're going to replace that with whatever x1 was, and here you're going to replace with whatever y1 was, and you're done. You'll have the equation. So let's do one example, right? Find the equation of the line through 3, -4, and 8, 6. So I've given you 2 points, right? I want the equation of the line through those 2 points. What should I get first? Calculate the slope. Why don't we label these? Let's label that x1, y1. Label this one x2, y2. I'm not even going to draw them. I'm not going to plot them. I'm just going to go straight to the formulas. So the slope is, by definition, y2 minus y1 over x2 minus x1. y2 is 6. Take away, be careful, -4. Right? You're taking away whatever y1 is, but y1's negative. So you have a double negative there. And then 8 minus 3, which is 10 over 5, which is 2. The slope of this line is 2. Is that what we're asked for, to find the slope of the line? No, you want the equation of the line. So now that I have the slope, I can go over here and say, hey, wait, I have a slope, right? And I have a point. I actually have 2 points. I can use either one, but I'm going to use this one. So now, using this formula, y minus, what's y1 for us? -4 must equal the slope 2 times x minus x1, which is 3, like that. And then this is y plus 4 equals, let's distribute, 2x minus 6. That's fine. That's the equation of the line. But I'm going to go ahead and get y by itself. Just going to subtract 4 on both sides. So y is 2x minus 10. That is the equation of the line. Now, just to verify, I'm going to go to Desmos, and I'm going to do a couple of things. First, I'm going to have Desmos graph the points, 3, -4. Then the point 8, 6. Those aren't coming out very good. There we go. All right, can you all see those 2 points? See those 2 points? Those are the points that we were given. And now what I'm going to do in Desmos is I'm going to type in the equation we just came up with. And we should see a line go through both those points. Y equals 2x minus 10. There it is. See, we have found the equation of the line through those 2 points. That's something that everyone here needs to know how to do, right? And all we're going to do now is we're going to adapt that same idea to this picture. Instead of doing it with 2 points, here's what we're going to do. We're going to take a function. We're going to pick 2 points. And then we're going to find the equation of the line through those 2 points. Once you know the 2 points, you just do what we just did, right? But the 2 points come from the function itself. It's not something that's handed to you directly like I just gave you. And when we do this, this line is called a secant line because it cuts through 2 points on a graph. Anytime you have a line that cuts through 2 points on a graph, we call it a secant line. All right, so let's do an example. That was just building up to the actual example. So I think I have it right there. There we go. Good. All right, so we have, let's use g. Is that okay? We'll use g of x. That shouldn't freak us out. G of x is 3x squared minus 2x plus 3. Part A. Find the average rate of change from -2 to 1. Okay, so what do I need to do? I don't need a picture, do I? -2 to 1. I'm going to get 2 points, right? First, I'm going to take -2 and plug it into the function, right? So I'm going to get some point. Let's do that. Let's do that scratch work over here on the side. So this is my scratch work over here. I'm going to do g of -2, which will be 3 times negative 2 squared minus 2 times negative 2. I'm plugging into the original function. 3 times negative 2 squared is 4. 2 negatives become positive. 12 plus 4 plus 3? 19? What is my, yeah, 19? Y'all agree? So at negative 2, we have a point here, 19. Now what? Plug in 1, right? Plug in 1 to the function. That should be a lot easier than the previous one. 3 times 1 squared minus 2 times 1 plus 3. 1 squared is 1. 3 times 1 is 1. So 3, take away 2, add 3. 4. So when we plug in 1, we get 4. Right? And just for fun, I'm going to go back to Desmos. I'm going to plot these points to see if they match up. We got negative 2, 19, nope. And then 1, 4. Where is it? There they are. So those are the 2 points right there. Right, those are the 2 points. And now I'm going to graph the function, which is 3x squared minus 2x plus 3. All right, so there's the graph of the function. Let me kind of stretch things out a little bit. All right, so we've got this function, right? 3x squared minus 2x plus 3. There it is. And we're trying to, the first question was asking to find the average rate of change between here and here. So we're going to try and find the slope of that line connecting the two, right? So what's the answer to this? This should be equal to what? Let me call on somebody. Philip. Where's Philip? Philip? Where? That's you. Okay, Philip. So, average rate of change on this now. No, just tell me what I'm going to calculate here.
F of B minus F of A.
Okay, so what's f of b for us?
F of B would be 4.
4. Take away
19.
19 over 1. Take away
Negative.
negative 2. Okay, good. Right? So that is our average rate of change. F of b minus f of a